So that's okay. Yeah. So thank you for that lovely introduction. As said in the introduction, my research focuses on stars and how their rotation evolves over their lifetimes. So rotation is one of the fundamental properties, one of the most important properties of stars like our Sun that we're interested in. It determines a whole bunch of things like how magnetically active the star is, and it also sets the kind of long-term evolution for the star over the course of its lifetime. Okay, so understanding the how and the why of why the rotation changes and evolves over the course of the star's life is something really important if you want to understand low mass stars like our Sun. Okay. Oh. Playing this game again. Aha! Okay, so this is a video of the Sun, and it's observed by the Solar Dynamics Observatory. And so using videos and images like these, as Stephanie mentioned earlier, we can determine that the Sun has a rotation period of about 27 days or so. And I think the gentleman who asked the question has since left, maybe, but he asked a very astute question of how can we determine the rotation periods of other stars? Because, again, as Stefano mentioned, they're point sources. We can't take videos of them to determine their rotation periods that way, okay? And Stefano gave a very... Nope. We can do it. Here we go. A very brief answer to that question, but what we can do is we can monitor the brightness of these stars over time because they have spots which are darker, and so these spots are rotating along with the star, right? And so if you have, if the side of the star that's facing us here on Earth is very spotted, the star will appear ever so slightly dimmer, but if there's no spots or very few spots, then it will appear ever so slightly brighter. And so you can kind of see this, nope, oh, it's very unhappy. Can I go backwards? It's just going forwards. Can you make it go backwards? Yeah, there we go. Forward one. Okay, so, and if you observe the brightness of the star over time, you'll see it brightening and dimming because of these spots rotating in and out of view. And eventually, this is what we call a light curve. Okay, and eventually you're going to see this pattern of brightening and dimming repeat because after one rotation period, you're going to see the same face of the star again. And so once that repeat happens, you know that's how long it takes to do one rotation. Okay, so you can measure the rotation period of a star this way. Now, this is a real light curve. It looks a bit messier than on the previous slide because in reality, spots, they kind of appear, they disappear, they change shape and size over time, so that, this looks messier than the kind of ideal cartoon sketch I showed on the previous slide. I should mention this is observed by the Kepler Space Telescope of this star charmingly named KIC 1995351. And even though it's a bit messier though, nevertheless you can still see this kind of brightening and dimming pattern. And if you just take the... No, I didn't want to go backwards. Am I using this wrong? One more. Yeah, there we go. If you take the measurement between kind of successive peaks, you can see that it has a rotation period of about 3.3 days. So we can use this technique to measure the rotation periods of lots of stars. And one of the places where we astronomers particularly like to measure the rotation periods of stars is stars in open clusters. Okay, so these are clusters of stars all located together in one spot. And the reason why we like clusters is because you can relatively easily determine the ages of the stars in those clusters. In fact, all the stars in a cluster should have basically the same age. Okay, so I'm going to try this again. You know what? I'm just going to say next. So this is potentially a bit of an overwhelming plot, but each of these panels represents a different cluster of stars with the age of the cluster on the panel. And on each panel, what's being shown is the rotation period of the stars in that cluster against the masses of the stars in that cluster. Okay, and I'm going to simplify this down a bit. Next, and let's just focus on these two clusters, which is the relatively young H Persei cluster, which has an age of about 13 million years. That is young in astronomical senses, and then this NGC 6819 cluster, which has an age of 2.5 billion years. Okay, and we're going to make a further simplification. For the rest of this talk, I'm only going to focus on solar mass stars, so masses with similar masses to our Sun. So let's just throw away the rest of these stars, and that's what we're left with. Okay, so if we look at the left, this H Persei cluster, we see that it has a spread. The solar mass stars in this cluster has a spread of rotation periods ranging from fractions of a day up to about 10 days, whereas NGC 6819 only has, the solar mass stars in this cluster only has a very narrow range of rotation periods, all clustered about just under 20 days or so. Okay? So what you can see is, even with just these two clusters, you can see that solar mass stars, their rotation periods evolve drastically from this young age to this older age. Okay, so let's look at more clusters. So again, we're only going to consider solar mass stars, and on this plot we have rotation rate on the y-axis. That's proportional to the inverse of the rotation period. So faster stars, or more rapidly rotating stars, are at the top, slowly rotating stars are at the bottom, and we have age along the x-axis, the age of these stars. And each of these vertical lines represents the range of rotation rates from one of those clusters I showed in the previous slide. And this kind of shows you kind of the evolution of what's happening. I think it's still a little bit confusing to interpret because we're dealing with distribution of rotation rates rather than individual stars. So instead what I'm going to do is I'm going to plot some some examples of individual tracks of how stars are moving through this diagram. Okay, and now that we have and these are numerical models that were fit to this data. And now that we have the models, I think they're easier to interpret. I'm actually just going to get rid of the data from this representation for now. But what we can see is that early on, stars are born with a range of rotation rates. So the blue curve is an example of a star that was born rotating relatively rapidly. The red line represents a star that was born rotating relatively slowly. And then the green one somewhere in between. And what we see is that early on, they all spin up. Their rotation gets faster with time. Then they reach kind of some point, and then the reverse happens. Their rotation starts spinning down. They start getting slower with time. And so you can kind of divide this plot into kind of two different sections. The pre-main sequence contraction phase and the main sequence spin-down phase. So let's go over what's happening in these two phases. So the pre-main sequence contraction phase, pre-main sequence stars are stars that haven't yet reached, let's say, their adulthood. They're still big balls of gas, they're still collapsing under gravity. And the reason why they're spinning up is because of something known as conservation of angular momentum. So, angular momentum is a fundamental property that all objects in the universe have. It's determined by how rapidly something is rotating, how massive that object is, and kind of the shape of that object. And because stars on the pre-main sequence, they're still contracting, their shape is changing, and if that's all that was happening, then their angular momentum would be changing. But we know that that's not allowed. And so to compensate for that, the rotation of these stars increases, it spins up, in order to conserve angular momentum. Now, a more familiar example of this in day-to-day life might be, you might have seen videos of ice skaters spinning on the spot, and as they pull in their arms and legs, you start to see their rotation get much, much quicker. This is exactly the same thing that's happening with these stars. Okay? Once they stop contracting, and once they settle down to their kind of the size that they'll remain for the majority of their life, we say that they've hit the main sequence. And on the main sequence, stellar winds take over as the kind of dominant mechanism by which angular momentum evolves for these stars. So stellar winds are a steady outflow of material emanating from the star into outer space. So the star is losing material into outer space. Stellar winds basically exist because of magnetic fields, which I'm going to explain with the help of this video. So this is a video of the Sun, again from the Solar Dynamics Observatory. And what you can see happening kind of on the left here, this is known as a solar flare. And what a solar flare is a rapid conversion of magnetic energy, so energy from the magnetic field of the Sun, into other forms of energy, namely light and heat. So you can kind of see this region here is brightening over the course of the video. And it's also a conversion of energy into kinetic energy. And so you can also see there's this kind of plume of material just here that's being released into space, and that's also a conversion of magnetic energy into kinetic energy. Now, solar and stellar winds are very diffuse. You can't take videos or images of them even for the Sun, but they exist ultimately for very similar reasons to this flaring. It's just a conversion of magnetic energy into kinetic energy, driving an outflow of these solar winds. So if we return to this plot, the stellar winds, because they're carrying the material away from the star, that material also has some angular momentum associated with it, right? And because the star itself is losing that angular momentum, it has to spin down. Its rotation has to slow down over time, which is what's happening in the second part of this plot. Now, something interesting is that, an interesting feature of this plot is that regardless of what rotation the stars arrive on the main sequence with, they kind of all settle down onto this relatively narrow sequence towards the end of their lives. And to understand why that's the case, we have to understand how stars generate their magnetic fields, which Stefano touched on briefly, but I'm going to kind of discuss from a slightly different angle with the help of this video. So this is not a star, you may be surprised to learn. It's what's known as a homopolar motor, which is a bit of a mouthful, but you can make one of these at home with some relatively easy to obtain materials. You just take a battery, you attach some magnets to the bottom, and then you connect the top and the bottom of the battery up with a wire. And because you've completed the circuit, you get an electric current running through the wire. And all electric current is moving charges, right? Moving electrical charges. And so it turns out that if you have moving electrical charges in the presence of a magnetic field, which in this case is being provided by the magnets, you can get a rotational motion. Could I get the next? So that's what this motor's doing. Moving electrical charges plus magnetic field gives you rotation. In some senses, a star is the reverse of that, okay? Because a star is made up of an ionized plasma, so it's just all moving electrical charges, essentially. And as we've already said, stars rotate, and so this combination of electrical charges plus rotation gives you the magnetic field. This is how stars generate their magnetic fields, right? Now, a star is much more complicated, at least when it comes to its magnetic fields, than a motor, but it's ultimately the same set of physics that's describing both of these systems, at least when it comes to their magnetic fields, right? But just to give you an idea of how much more complicated it is, this is a computer simulation of a star similar to our Sun, and the aim of this simulation was to show or to attempt to explain how magnetic fields are generated inside of stars. You can see it's really complicated, it's constantly evolving over different length scales and time scales, and actually we still don't fully understand all the physics going on with magnetic field generation for stars, and this is an active field of research. It's not my field of research directly, but yeah, there's lots of people studying this. Okay, so if we come back to this, and what I've said is that rotation is basically driving the generation of magnetic fields, and it turns out that stars that are rotating more rapidly generate stronger magnetic fields. Okay, so what we have is, if you take the blue star, it starts its main sequence life as a relatively rapid rotator. That means it has stronger magnetic fields. That means it drives stronger winds, which carry away more angular momentum from the star, and so it spins down faster. Whereas if we consider the red line, that star enters the main sequence rotating relatively slowly, so it has weaker magnetic fields, it drives weaker winds, and so it's losing angular momentum slower. Okay, so this blue star, even though it started off rotating much more rapidly, it's also losing angular momentum more rapidly, and so it catches up with the red star, such that they all eventually converge onto this narrow sequence. And this is really nice because it allows us to use a technique known as gyrochronology. Now, earlier I mentioned we like open clusters because it's relatively easy to determine the ages of the stars in those clusters. But what about stars that aren't in clusters? If you try to use traditional age determination techniques with stars that aren't in clusters, they just don't work very well. But what you can do, at least for older stars, is gyrochronology, because at this phase of the evolution, it's basically a one-to-one relationship between the rotation of the star and its age. So if you can measure the rotation period of the star, which is relatively easy to do, then you can have a relatively good estimate of its age. So I've basically gone through all the different parts of this diagram, and I don't want to give you the impression that we understand everything there is to know about how stars rotate and their evolution over time, because we don't. There are still many open questions. So just to wrap up this talk, I'm going to go over just one of the open questions that currently exists, which is that recently there have been new observations of stars, older stars, that don't match the models, which are these ones in the bottom right-hand corner here. And you can see that they all systematically are rotating faster than the models predict. And so you might think that, well, the models are wrong, they definitely are. And you might think that we need to adjust the models in sort of this kind of a fashion, where you'd want to kind of bring it up slightly. And I mean, this looks like a relatively small adjustment, but this tells us that fundamentally there is something wrong with our understanding about how stars generate their magnetic fields and generate stellar winds, and how they're losing angular momentum for stars at these much older ages. So this was a really exciting result when it first came out, and we still don't really have a good explanation for it. And with that, that's kind of everything. So yeah, hopefully you now have more information, more knowledge about how stars rotate, and kind of a flavour of the kind of questions that we still don't know the answers to. So thank you very much.
Questions for Victor? In the back left.
Yes, thank you for your talk. I was wondering, your models are based on how many stars that you have observed, that have been observed?
Thousands, if not more. Yeah, thousands, on the order of thousands.
Oh yeah, okay. Thank you.
Oh, are you picking or am I picking?
Also in the back, yes.
First, thank you for presentation. And second, by evolution, do you mean the progress, like orthogenesis, or kind of another kind of evolution altogether?
Yeah, I don't mean in the biological sense. I just mean how it changes over time.
So it's by chance.
If by
chance, I mean by time, it is a different kind of evolution, so something like that. It's not progress, yeah.
Yeah. How's
Okay, so it's not progress, just different time, different approach, yeah.
different approaches
Yes.
to?
For example, I didn't get what's the meaning of evolution there, to be honest.
Okay, so all I mean by, so when I say rotation evolution, I just mean how the rotation of the star is changing as time progresses.
Yeah.
Victor, thank you for the talk. Maybe a silly question, but
No silly questions.
I'm not an astronomer, but how do you know it's the rotation that creates the electrical field and not the other way around?
Lots of equations.
Okay.
Um,
Mathematically, would it not be equivalent?
How do I know it's... Why would it be equivalent?
More electric and less rotation.
No, it's a question. Would it not be equivalent if you switch the equation
This
around?
is much more philosophical than something I was expecting.
The angular momentum comes from the accretion of the solar, well, the accretion of the star, though, right? It's not
Yeah, so, that's exactly it, actually. Like, regardless of, even if the star didn't have a magnetic field or electric currents or anything, it would still be rotating.
As opposite to the motor you showed.
Yes.
Okay.
Good save.
Then,
Yeah. Can you explain a little bit more the previous slide? Like, so you measure the rotation, and how do you know which is, if it is red, green, or blue?
These are just examples. So,
But you measure the rotation, and how do you know the age? Is my point. Like, because if you measure the rotation, could be any of the three, for instance.
right, okay, so could you go back to the slide with the data and the...
Oh,
Yeah, that one.
this,
One more? Or, well, next. And then put, yeah. Okay, so if... Oh, no, bring back the lines. I can't use this thing, I don't. So this is the data that we have, right? So we have distributions of rotation periods, and we know the ages because, oh, we can get into that, but that's a different explanation. We can measure the ages for stars and clusters. So essentially what we're trying to do is fit individual stars to this data, right? Now, the assumption that we make is that you know, the fastest star in this cluster will also correspond to the fastest star in this cluster will also, so that, you know, the lines won't cross,
Okay.
right?
So these vertical lines are clusters.
These vertical lines represent the rotation rates of all the stars in one cluster.
Okay.
Did that answer your question?
Yeah.
Yeah, okay.
Yeah. Thank you.
One last.
thank you.
Mine was just to add to this. Is this a comprehensive graph here? Because you can see as you get to older clusters, you've got very little data.
Right, so, and that's because clusters, they eventually disperse over time, so there's very few old open clusters. And this is actually the sun, so it's not even a cluster. This is one data point, it's not a distribution of stars. But nevertheless, there's a lot of the physics driving these models indicates that this should be the case. So there's a lot of other measurements that go into these models as well, things like the magnetic fields of stars and how they change with rotation rate and how the stellar winds change with rotation rates and things like this. So the rotation data is one set of constraints on these models, but there are actually other constraints coming into this model as well that I don't have the time to talk about and kind of don't really fit the theme of this talk anyway. So yeah, there are more constraints here than it seems like from this plot. But that's why when they don't fit the data that I mentioned in the last slide, it was so surprising. It's like, oh, it's not just this data, it's like we have to reevaluate a whole bunch of other things as well.
Okay, we have time for one more.
I can ask him tomorrow, it's okay.
So you showed on the last slide some outliers.
Yeah.
But if your last point is only the sun, how many other points do you have in the right part that supports your equation?
Right, so the last point was only the sun, yes, but as I mentioned for the previous question, there are other constraints that I wasn't showing on this. So, but like a lot of them, kind of the constraints stop here, right? And then these are the, say, most recent observations. And so this part of the evolution, before we had this data, was sort of an extrapolation. of the data from younger ages. So the fact that this was doing this was so surprising. So you're right, it's like before this data there wasn't really any kind of constraints in this part of the diagram.
So
now
the,
we're
the last point before the yellow ones is the sun, or not?
yes.
Okay.
Yeah. It's our most well-known star, so it's pretty trustworthy. But yeah, like we still don't exactly really know what's happening with these stars, and it's kind of a lot of work's currently being done to try and explain them.
So this outlier where the age was measured with other technique than this one? The outlier's age was measured with other technique, right?
Yes.
Okay.
Something called astroseismology, if that means anything to you. But that's a whole different talk.
Okay, thank you.
Okay, so that's all we have time for right now. Let's thank Victor again. You could stay here, Victor, and Stefano, you could come up as well. We, the organizers, like to thank
Huh?
the
What's this part?
people who volunteer to give talks.